I should be able to count on you being able to tell me what a normal force is by definition, what a tension force is by definition, and what a resistive force is by definition. You should have a definition for all of those. Specifically as well, you should have this one broken up into two categories: friction and drag. And that's about where we left off. There's a few other things that I would like to discuss real quick, and to me this is just stuff you should already know. First, units. The Newton is the unit of measure we will use for measuring force. The Newton. Its English standard unit that is similar is the pound. Both of these are units of force. We will focus 100% on the Newton. And from Newton's second law, a Newton is a unit that is coupled together, combined together. It's a complicated unit. It is a kilogram meter per second squared. It is incredibly important to me that you know how to break a unit down into its parts. In this class, every unit we will see can be broken down into kilograms, meters, and seconds. Very seldom do we step outside of this boundary. So almost everything you will see will be in these. So although we will have lots of other units we will discuss, they're all named for some combination of kilogram, meter, and second. Be able to speak to them, because this year I intend to do a pretty robust challenge of your skill set when it comes to looking at the units of your answer. Meaning we should be able to solve something that is all symbolic, and you should from there be able to figure out if the units of that symbolic solution work out to the appropriate units that we're expecting. So when we solve for something using Newton's laws, you should expect the result should produce kilograms, meters per second squared. Now, it's not a big surprise where this comes from. This comes from the fact that Newton's second law, which says that the net force on a system is equal to MA, suggests that our answer is going to be kilograms, meters per second squared. However, this is not how Newton put it. Newton was a little different in the way he formulated this. We teach it this way now. But Newton didn't actually put it together like this. He put it together as a derivative. He said that the net force was related to the rate of change of momentum. And I would expect you to be able to know why this is an important distinction. And maybe not today, because for some of you this is your first trip through this. But in a couple of weeks, we should come back to this and understand why this distinction is important. And just to give you a taste of it, Newton never assumed that mass was something that would be constant. Newton assumed that mass would change, that mass was connected to acceleration. No better way is there than thinking about a rocket or an automobile, where its acceleration is related to the rate at which the fuel is consumed. And therefore, as you consume fuel, your mass changes. Newton was also able to anticipate that collisions could occur that would change the mass of an object. And therefore, he never assumed that the mass of a system was constant. Which is why this formulation actually is more valuable than this formulation. We teach F equals MA to students who are just being introduced to this topic because it helps to have the object stay the same all the time. The ball bounces off the wall, you push on a cart, a block slides down a ramp. We don't assume that the block is leaving bits of itself down the ramp. That makes for a more complicated arrangement. So, I want to make sure that I've at least done this once so that I can say with a clear conscience, I believe you know how to do this. So let's do this just once and see if I'm right. You might want to write some of these details down. A 60 kilogram sprinter goes from 0 to 12 meters per second. In 10 meters. What net force acts on them? Again, a sprinter with mass 60 kilograms goes from 0 to 12 meters per second in 10 meters. Assuming uniform, what net force acts on them? I'm going to not try and insult your intelligence too much, but I am going to let you know that my expectation was that you knew you needed the acceleration for this. Assuming uniform, you were able to pick a relationship that probably could have gotten you the acceleration. And you needed the acceleration because by definition, net force equals ma. In order to figure out the net force acting on an object that is accelerating, we need the m part and we need the a part. This is not a particularly interesting question, by the way. In fact, I would say that this is one of the least interesting questions there is, but this is kind of the straightforward stuff. This is, if I know the acceleration and the net force, you tell me the mass. It boils Newton's laws down to something that is not Newton's laws. This is not Newton's laws. F equals ma is not the way I want you to think about it. However, in this problem, that's how you got to your answer. The truth is, though, I'm repeating the word net force when I say that. And the word net force requires the summation ahead of the F. Net means to sum. And so a shortcut to saying the sum of all forces is to say net force. Be careful when you see the word net force anywhere in your homework. And definitely be careful when you see it on the AP exam. When they say net force, they are not talking about an individual or particular force. How many forces do you think are acting on the person during the time that they're accelerating? Name at least one. Gravity. Okay, let's begin there. This point, you guys should remember Freebody diagrams from last year. If you don't, I'm going to start treating you like you do remember and take my little person and reduce them to a dot and start considering the forces acting on them. The person is interacting with the earth. There is a force of attraction between their masses. So yeah, I expect that there is a force of weight acting on them. It will be acting straight down towards the center of the earth. It exists as long as they're close to another object that can exert a force of gravity. Is this the force that's accelerating them forward? No, it's unlikely that this is it. Name me another force. Yes, ma'am. The normal force from the ground. Sure. How would I draw that here? So I will draw an upward arrow to indicate the normal force from the ground. By definition, normal forces are perpendicular to the surface in contact. It wasn't stated that the ground was horizontal, but I don't think that's an unrealistic expectation for a sprinter. Is this the force that is causing the person to accelerate forward? I sure hope not, because it's pointed upwards. Name me another force. Jake?
The friction of the feet on the ground.
All right, what direction should I draw that arrow?
Backwards. To the left, I suppose. Or to the right.
Now, I think most of you would have drawn this force to the left. In fact, I think that that would be a pretty safe bet. But it's friction that propels the person forwards. If you don't believe me, if this were a slick surface, would their foot have caught traction on the ground? And if it was ice, and they tried to pull their foot backwards, what direction would it have gone? Backwards. What direction must friction hold on to their foot in order for that foot not to be drawn backwards by the action of their muscles? Do you understand what I'm trying to tell you, right? It is friction that propels this object forwards. In fact, it is friction that accelerates this object. Now, that's created by the act of them trying to draw their foot backwards. But understanding the direction of friction might not always be as clear-cut as it was last year. Does everybody understand? And I'm going to mess with this quite a bit in the next couple of weeks. There is probably another force here. Yes, sir? Yeah, I'd probably draw the drag force. What direction do you think I should draw it? I believe that that's not inappropriate to think that the force of drag would be backwards. Clearly not as big as the frictional force, or else they'd be propelled backwards by the frictional force. All right. There may be other forces at play here. I think these represent the basic forces. I don't think there's anything else that's in contact with the sprinter that I need to bring up, but this is a start. A free body diagram should have at its core these basic properties. A dot to represent the entire mass of the object. It should have individual arrows that indicate the direction of the force acting on the object. Those arrows should be initiated on the dot and drawn outwards. They should be drawn in the direction that they act and proportional to their respective sizes. I am going to be terribly brutal on free body diagrams this year. I am every year in mechanics. You will be required to draw a free body diagram on the exam. It will be critiqued, and you will probably get between 2 and 4 points on an FRQ for your ability to draw a clear free body diagram. Now, you have to understand, those are the easy points. You've got to get them. So, normal forces are perpendicular to the surfaces, period. No matter what you think they're doing, you must draw them perpendicular to the surface. Don't violate that rule. Be careful, though. There's ways for you to be fooled here, and I'm about to try. Second, tension forces must act in the direction of the conduit, and only in the direction of the conduit. Third, frictional forces can only act parallel to the surfaces in contact. They can only act parallel to the surfaces in contact. That doesn't mean you know what direction they act, however. It just gives you a binary option. And last, drag forces act in opposition to velocity. Drag forces act in opposition to velocity, which means they are not dependent on a surface. Let's look at our next example. And in this example, I am actively trying to trick you. All right. I have a box at rest on an incline. A box at rest on an incline. I would like you to draw all the forces acting on the box. What's the first arrow you should have drawn? If you remember what I talked about from last year, and that's not all of you, I know, but what is the first arrow you should always draw? It should always be gravity. Always gravity first. And I'll tell you why. You're going to scale the rest of the arrows based on gravity. So in this class, we draw gravity first, and we base the rest of our forces on the size of that arrow. So draw a clear arrow here, one that gives you a sense of size for everything else. Make sure it is drawn in such a way that it is straight down. Be careful to align it appropriately with the horizontal. When you draw that arrow, be cognizant of its size, because you're going to draw probably the normal force next. It would make the most sense. But in your head, you should be thinking, I need enough upward force to make sure the box doesn't move upwards or downwards. Our forces are going to be broken up into components later. You know that's coming. But I need to know that there is an upward force that's at least as big as the downward force from gravity, because the box doesn't go up or down. However, there is no force that is straight up. The next force you're going to draw is normal. Which is likely going to be drawn something like this. It must be perpendicular to the surface in contact. So it must have that look to it. More appropriately, it makes up only a portion of the upward force acting on the object. It can't be bigger than the weight of the object. So we know that there's probably a third force. And I don't think anybody has a problem drawing the third force. It should be friction. But when you're drawing the size of the frictional force, you should be using two things to help you draw it to scale. The box doesn't move. So there should be a, oops, I don't want to do that. There should be a portion of the force that's about that long, that when added to the other force's length equals the length of the gravitational force. That should be the first thing you're keeping in mind, that the upward component of the frictional force and the upward component of the normal force work together to keep the box from going downwards. But second, and this one might be easier to look at, the size of the normal force to the left should be balanced by the size of the frictional force to the right. The box doesn't move, so all of these are in balance. So when you draw your free body diagram, that's the level of precision I will expect every time. So when we grade them, there will be statements of, are they drawn to an appropriate size? That's the bar by which you should be drawing your arrows. I do not need you to measure them out and calculate their size, but a simple little run through like I just did should be enough for me to know that you have taken it into consideration. Also, this is a sharp right angle. Every grader on the planet who's going to grade your exam is going to be looking for it. If you know that two forces are always at right angles to each other, you had better draw them at right angles. I'm saying that enough to believe that you might want to take out a protractor and make sure they're at right angles to each other.